This would actually be really difficult. I wish I had another machine. Yeah, the front panel's not coming up. Yeah. Well, make this easy. Kill time because I was up until 4 a.m. last night working on this, so yeah. Finish. What the hell is that? Of course it starts out minimized. Ooh. It's the wrong one. There we are. There we are. Yeah, I noticed. Okay, well. Yeah. Okay, well, fuck it. Maybe we can use a sidebar. Yeah. This is not this good. Okay. Well, sorry about that. My name is Matt Joyce. Hi. I'm sorry for the delay. As you can tell, I didn't actually expect this machine to completely foul up this bad. So, the art of DoFu. The question is, that I get it from a lot of people, is what the hell is this talk about? So, obviously it's about data analysis, which that's not obvious at all. So, there's a lot of different components that go into data analysis and a lot of different fields that deal with it. Data mining is one that a lot of people like to talk about in security. Statistics, inference, there's a ton of different mathematical equations used to sort large volumes of data. And there's done a ton of different scientific fields that deal with it. So I wanted to give a talk that kind of briefly touched on how to deal with large quantities of data and explain to people just how dangerous it can be that there's a lot of large quantities of data out there that we can all access. So I also wanted to make sure that it was kind of entertaining. I'm sorry, thus far I've been incredibly boring, and that's my fault. You can all heckle me. Thank you. So, I've covered most of this. Does anyone want to know what inference is? Okay. Yes. Okay, so inference algorithms are basically learning algorithms. They infer things. They make assumptions, and then they make predictions. Inference. So 80% is showing up. This is obviously not true. I'm going to fail horribly. It's all breaking apart, and I'm imploding inside. This isn't going to teach you statistics. Statistics is really fucking hard. There's a lot of math that goes into it. There's a million different specialized equations for solving specific data sets. The idea here is coming up with a single set of data sets that can sort a large volume of data quickly and efficiently. That doesn't mean sort it right, which brings us to our next slide. Enrico Fermi. Now, you can't really read that, but basically, Enrico Fermi is this guy. What? F5? Yeah, it's... Yeah, exactly. Yeah, so I'm going to just not do that because my machine is about to fall apart. And I'll just cover it with my, my voice, and hopefully this all makes sense in the end. When I get the applications up, it'll be okay. Enrico Fermi saw the first atomic bomb drop. The anniversary was 3 or 4 days ago. He's also known for a sort of type of math called Fermi math. Fermi math is usually taught to children. And the reason is because you can deal with very large sets of data, very large numbers, and you can solve things relatively quickly. So the story that's famous about Enrico Fermi is while everyone else is watching the bomb explode, he's dropping pieces of paper. And he's watching the paper waved in the wind, and he's actually calculating the blast yield from the bomb. So small volumes of data, in some cases, with the right brain, the right causalities and correlations, you can figure out cool things. In this particular case, you can figure out the blast yield of a bomb by watching paper fall. So data analysis is all about doing shit like that. Seeing something that looks seemingly unrelated to something else, but finding a correlation and defining a predictive causality. Doesn't have to be right, doesn't have to be correct. We're not scientists, we're not writing PhDs. Most of us are in the security field or we're hackers. We're looking for a solution to a problem. That problem might be, how do I break into this website? Or I'm doing a search on my own network and looking at all of our own CVS code, and I want to make sure that my developers aren't doing something stupid, like using usernames inside their application based off of, let's say, the name of the application. So, ethics. Some of you have them, some of you don't. When dealing with data analysis, it's very dangerous. If you look at data analysis the wrong way, you can basically confuse people. You can analyze things and do things like racial profiling and say that all Arabs are terrorists. That's not true. Most Arabs are very nice people. They're good people. But there are a large number of terrorists in the world who happen to be of Arabic descent. Therefore, racial profiling works on paper, but in reality, it's not fair to people individually. That's ethics. Be ethical, don't be a douchebag, unless, of course, you have no ethics.
Or you're an American.
Or you're an American, because we rock and we have manifest destiny and we can do whatever we want. The datum. What is data? Where is data? Basically, what I'm coming down to here is how can we catalog data? How can we capture data? Data exists everywhere. Knowing the number of people in this room, knowing the number of people with certain types of colors of eyes, knowing genetic information, knowing the temperature of the room, knowing how many lights are in the room, how many sockets, how many doors, how many windows, how many everything. Data's everywhere. How do we catalog it? What data do we want to go after? Is it relevant to what we want to search for? So, we got a little picture of Turing dressed up as the alligator hunter guy. So, trapping data. A lot of people for trapping data will use things like, with the AMD project, you're basically coming in here and they're saying, hey, you got this cool nifty badge, if you want to use it, give us some information about you. They're trapping your data, collecting it. There's other ways of trapping data because data exists in the wild. Things like, and we'll get to them, CVS repositories are online, there's code online, there's websites with lots of information. I don't think it's Eventbrite, but there's something like Eventbrite for if you ever go biking or running or you're in a marathon, these guys take pictures and they match it up to your number on your chest based off of an OCR algorithm. So if you know someone's name and they're into this sort of thing, you can pull pictures of them online. So there's a lot of data out there, and it's pretty easy to find. If you're looking for something in particular, you'd be amazed at what you can find out there. Spidering mailing lists is one of the things I was looking into. It's readily available, it's basically pretty obvious, and it helps us understand communities. There's a lot of different mailing lists out there, they're all open, LKML, NILUG, NYC Resistor, all this stuff. And I wanted to do some experiments to show you that even in a cultural setting or a societal setting, you can see how analyzing data can be efficient or inefficient, as the case may be, in defining correlations. Is there a correlation between the size of a mailing list, the size of the emails, the number of people on the list, the content of the list, and does that correlate to the success of the project or the failure of the project? As it turns out, most of the case, that's not true. There's really almost no correlation in that stuff. Yep. So extrapolating data is really not that hard. You find a large data set on the internet. For instance, the schedule of talks on the website. I'll actually demo a little bit of, well, show you a little bit of a script that can do this, but you look at the talks on the schedule of talks. The way it's broken down in HTML allows you to very easily extrapolate all that data and dump it into either a database or a flat file that you can easily sort, and enter into applications for data mining. Extrapolating data is easy. Perl is great for it. This is my troll post. There's a lot of people who hate languages. Don't hate languages. Some languages are actually pretty useful. Some aren't. Perl is very useful at parsing large volumes of data, and there's a shit ton of modules written for it for dealing with Bayesian algorithms, largely because of things like spam assassin and neural network programmers being lazy when it comes to parsing data. There are other languages as well that are really good. C is really good. That's actually bullshit. Lisp is also really good. I just wanted to piss off the Lisp programmers. Again, this isn't about math. There's a lot of math in this. It's about getting it done. You don't need to know statistics to use this stuff. The simple fact is, a guy who's into computer security probably knows jack shit about statistics because he didn't go to school for it. He went to school for other things. He's not an economist. He's not a mathematician. Well, he might be. I know a couple of mathematicians who are into the field. But in most cases, if you're actually dealing with auditors, auditors are not brilliant people. They're people who are technically gifted, and they're good at finding bugs. That doesn't necessarily mean that they're scientifically brilliant. Finding a bug in a data structure that isn't really logic, but is, say, a correlation, great word, is something anyone can do without having super huge amounts of knowledge regarding statistics. Probability. There's two basic types of probability that we're going to discuss because we're doing a linear analysis, is forward probability and reverse probability. In one situation, you know the outcome. In the other situation, you don't know the outcome. So in forward probability, you don't know the outcome. In reverse probability, you know the outcome, but you don't know some of the variables going into the data set. With reverse probability and forward probability, usually this feeds into Bayesian algorithms. How do you want to solve it? What are you trying to predict? Are you trying to predict members of the data set or outcomes? Regression is very simply explained. Gauss is a famous guy because he claimed to have invented basically the first linear regression algorithms. And the reason that he's credited with it is because he helped a guy track a comet back in the 1700s. Late 1700s, 1795, 1800 area. A man lost a comet he was tracking behind the sun. Back then, you didn't have a lot of ways to track celestial bodies. So they were trying to guess where it would reappear again. They had this man's record of where he saw it and tracked it in the sky, which wasn't exactly correct. But he was able to graph it, and basically, with regression, you'll have a graph with data points on it, and you draw a line through it and try and define a function that defines how that data set can be modeled. With some things, especially astral bodies, it's really easy to get a very clean line and follow it through to where it's going to appear. It worked. So least squares is what we usually use for linear regression. It's pretty straightforward. Most of you who have done calculus or worked in a lab in college have probably done this, whether or not you know it. It was probably brought up in your lab class whenever you needed to do a linear regression, even if you didn't know you were doing linear regression. Correlation. So correlation is basically once you have two sets of data that you've linearly regressed, you can try and see if those waveforms, those functions, match up in any way. If they match up in any way, they may correlate. They may not, but they may correlate. And if they do, you might be able to find something out that's either a third factor, or you might just be finding out what you wanted to know. So that brings us to the next slide. Correlation is something that's usually used improperly. It's one of these things that's great about statistics is you can lie really, really well using statistics. Throwing numbers at people tends to shut people up and dump them into idiot mode. There are fallacies about correlations that are pretty straightforward. Sometimes, just because a waveform matches up with another waveform doesn't mean that one's the cause of the other. It just means that these things match up. There could be underlying causes, data sets that you're not actually taking into account. Or it could just be coincidence. It's unlikely, but it could be. Other things that run into a problem with correlation is when you graph stuff, sometimes you'll see it, it's very obvious when you graph it, that sometimes the way the waveform